It looks like every time we do a calculation involving a new mass and its corresponding displacement, we're computing a slightly different value for k. Does that mean that the spring constant is actually changing a little bit every time that we hang a weight on the spring? Well, probably not. It looks like there's a process at work that's causing our measurements to be slightly off every time we make one. A good first step whenever we're trying to figure out what's up with our data is to plot it, to look at it visually, and to see if we can spot what's going on. In order to figure out what's going on, we're going to have to look at the data. And here's a couple Python procedures to help us do that. The first procedure here, getData, its job is to read the data in from a text file where we've entered the data. So it opens the file, and the first line of the file is just a header line that describes the format of the data in the rest of the file. We don't need that here, so we'll read in that line and discard it. And then for all the other lines in the data file, we'll read each of them in. They come in as each line comes in as a string, and then we're going to take that string and split it into substrings that correspond to the non-blank portions of the line. So the first substring is the first non-blank portion of the line, which will be the data measurement, and the second substring is the second non-blank portion of the line, which is the mass measurement. We then go off and convert those two strings into floating point numbers and append them to the appropriate list that we're using to accumulate the results. And when we're all done, we return the masses and the distances in two separate lists. The plot data routine is now takes over, and its job is to plot the data. So it goes off and first reads in the data. And the reason that we've separated the reading in of the data, the I/O, from the analysis, or in this case the plotting, is in case the format of the file changes, of the data file changes in the future, we'll only need to rewrite the getData portion of the Python procedures. The first thing we do once we get the data is to go off and convert it into the pylab array data type, a very handy data type for doing numerical manipulation. And here we see an example of how handy it is. On the next line, we want to multiply each element of the xvals array by the gravitational constant. In other words, what we're doing is we're busy converting the masses that we measured into the forces that they applied to the spring. And this statement here, an array times a constant will multiply each element of the array times whatever that constant is. The rest of the procedure goes off and then creates a plot, plotting the forces applied against the distances measured. The data points will appear as little blue circles, so the B means please make it blue, and the O is please make them a circle. Let's run it and see what the data looks like. Here's the results. We can see we get the sort of plot that we might expect. The x-axis is the force that was applied to the spring. The y-axis is the displacement we measured. And here are all the data points that we measured from applying everything from the 10th kilogram up to the full kilogram weight. Let's see what we can make of that. So is this what we were expecting? Well, our hypothesis tells us that this should be the relationship between the weight and the extension that we measured. That implies that if we sort of solve this for the extension, that we expect it to be the mg, which is, so this guy here is the force, divided by the spring constant k. So that means that what we expect, so all the measured points to fall on a line with slope 1 over k. Graphically, what that would mean is that we'd expect to find some line where that had all the data points on it, and the slope of this line should be the inverse of the spring constant. At least that's what this equation here is telling us. Well, that's not quite what we got. Let's see if we can figure out what went wrong. So what did we expect was going to happen? Well, we have this theory. So we have this notion that there's a linear relationship between the force that we apply, so here's a particular force, F sub I, and the observed extension. So we have this prediction, so this will be our prediction for the ith force, and our prediction for what the offset should be is equal to the force divided by the spring constant. So this is a line of slope 1 over k. Well, what actually happened is we have some measurement up here, and that measurement differs from the prediction by a certain amount. So here's my ith observation. And
there was clearly some sort of error that crept in. And so if we have this sort of model that what really happened was here, but because of some error in our process, we actually made a slightly different observation, maybe we'll make some progress if we think of it that way. So here's the error, and that's the difference between the ith observation and the ith prediction. So the question is, what can we know, what can we say about what our expectation is for those errors that are creeping into our measurements?